So suppose we have a random variable, let's call it x. Let's see here, x. And we know that x follows a normal distribution. We don't know the mean of x. We're going to call that mu. And suppose that we know that the standard deviation is 1. So x is distributed normal, mu, 1. We want to take a sample of x, say that x sample is 4. First it turned out to be 4, and then we rolled the dice again, and then it turned out to be 6. We want to use this sample to estimate mu here. And we're going to use, the method that we're going to use is the method of maximum likelihood. Maximum likelihood. So, well, first, I guess, just intuitively, what would you guess is the mean of x, or the expectation of x, given this sample? Well, our best guess would probably be that the expectation of x, mu, is 5. It's the sample mean. That's going to be our best guess for mu. Can't do better than that guess. And we're going to prove, we're going to write a proof of this. So the method of maximum likelihood works like this. We say, what's the likelihood of seeing this sample? Well, it's, you're thinking about R, so we're thinking about the PDF of the normal distributions is, we can find it with dnorm. The density of seeing 4 given a specific mu times the density of seeing 6 given a specific mu. We're gonna write down the math equation for this. This is the likelihood of the sample. And then we're gonna choose mu in order to maximize this likelihood. Choose mu to maximize likelihood. So what's the density of the normal distribution? We have an equation for that, and let me bring it up here. It is, looks like this. The PDF, normal distribution, is 1 over the square root 2 pi, and it's supposed to be sigma squared here, but we said our standard deviation is 1. So I'm just going to not write the sigma squared. And then exponential function, so e to the this, that's x minus mu squared in the numerator divided by 2, and again, it's multiplied by sigma squared, but again, our sigma squared is 1. I just won't write that. So that's the density of the normal distribution. And we're gonna say, what is f evaluated at 4? Just what I wrote here, I'll highlight it. Times f evaluated at 6. And then we're gonna think about how we could choose mu to maximize that likelihood. So evaluated at 4 goes like this: 1 over root 2 pi times x 4 minus mu squared over negative 2 times 1 over root 2 pi x and then 6 minus mu squared over negative 2. I can simplify this a little bit. I have these two things multiplied. In the denominator here, I'll have root 2 pi times root 2 pi. So that'll just come out to be 1 over 2 pi. And then here I have like e to the a times e to the b. That's equal to e to the a plus b. So move this down a little bit. I can also write this as x. It'll be 4 minus mu squared plus 6 minus mu squared all over negative 2. And then things are getting a little bit hairy, so I'm going to use a trick. The trick is Oh, I guess before I introduce that, this again is the likelihood of seeing the sample for 6. And then we want to choose mu. Mu shows up here and here. The idea is we want to choose mu to maximize this thing. And the way we would do that is to take first order conditions, find the partial derivative of this likelihood with respect to mu, and set that equal to 0. Find the maximum. If it looks like this, then at the maximum, the derivative will be 0. That's the idea. The thing is, finding the derivative of this is a little more complicated than it needs to be. So I'm going to use the trick that I mentioned earlier. I'm going to take the log of this thing. So log likelihood. And log is a strictly monotonic transformation. So the maximum of the log likelihood will be the same as the maximum of the likelihood. Just the maximum of the log likelihood lets us get rid of that that exponential function in there, and make our computations just a little bit easier. Add a new page here. So what is the log likelihood? It is log 1 over 2 pi plus the log of the exponential function of this, which just simplifies to being this thing. So I'll just write 4 minus mu squared over -2 plus 6 minus mu squared over -2. And again, I'm going to take the derivative of this, and now it's the derivative of the log likelihood function with respect to mu, and then I'm going to set it equal to 0. So let's take the derivative. This part doesn't have a mu in it, so that just goes to 0. And then let's use power rule and then chain rule here. So this 2 goes out to the front for the power rule. So I get 2, 4 minus mu, and then just to a 1, I decrement the exponent by 1. And then I use the chain rule. Mu is multiplied by a -1, so that -1 comes out here, divided by a -2. And then the same thing for this term, 2, 6 minus mu to the 1 times -1 over -2. The 2's cancel here. And you can also see I'm multiplying by a negative and then multiplying by a negative again, so that would cancel out. So what I'm left with is just 4 minus mu plus 6 minus mu. And again, I took the derivative, the partial derivative with respect to mu, and then I'm going to set it equal to 0. So all of this is equal to 0. And simplifying a little bit more, I get 10 is 2 mu, or mu is 5. And compare that. What did we do here? We said, what is the value of mu that maximizes the log likelihood of seeing the data that we did of 4 and 6? Our guess was that x had an expectation of 5, because that's a sample mean, and then we proved it mathematically. So hopefully that was clear.